Support handout number 14. So in problem 1, we want to solve each of these equations using the factoring method from algebra. The way the factoring method goes is you get a 0 on one side. That's been done in all of these examples. And then you factor the other side. In part A, the factoring method that I will use is pulling out the GCF. Both terms have a common factor of x that I can pull out to the front. And then the reason we had that 0 on the one side is now I can take advantage of the fact that if you multiply two items and the answer comes out to be 0, the only way that can possibly happen is if one or the other of those items is equal to 0. And so I set each factor equal to 0, solve each little equation here for x, and I will have my solutions. There will be two solutions to this equation. Obviously, one of them is 0. And the other one, I'm going to subtract 4 and divide by 3 for a second answer of -4/3. So final solutions would be 0 and -4/3. Letter B, same technique here. Got the 0 on one side, need to factor the other side. I don't have a GCF. I see three terms, which makes me think this was somebody's FOIL problem. The only way you're going to get a 2x squared in the front is a 2x and an x. The only way you're going to get a 3 in the back, this 3 here, is a 1 and a 3. Now, I do need to give some thought as to where to put the 1 and where to put the 3. I know I'm trying to get a +5 in the middle. This negative sign at the end tells me that I'm going to use numbers with different signs. In other words, a +1 and a -3, or a -1 and a +3. What I'm thinking to myself is, if I put the 3 here, that seems good because then the outer multiplication will make a 6x. And if I put the -1 here, then the inner multiplication would make a -1x. Well, -1x plus 6x gives me that 5x that I needed. All that's left then is set each factor equal to 0. 2x minus 1 equals 0, x plus 3 equals 0. Solve each of these little equations for x, and we've got it. This becomes 2x equals 1, divide by 2. Looks like one of the answers is 1/2, and the other answer is -3. So my final two answers, +1/2 and -3. Part C, same idea. So I look at the left side. There's no GCF. There's not three terms, but there are two terms. And what I see is a minus sign in the middle and then two perfect squares. 9x squared is 3x times 3x, and 25 is 5 times 5. This is a difference of squares, so it factors in that a plus b, a minus b pattern. I'm going to have 3x plus 5 and 3x minus 5. If you FOIL that out, you'll get back to what we had. And then the finish is basically the same. Set each of these factors equal to 0 and solve for x. 3x equals -5 here. 3x equals +5 here. And then divide everybody by 3. It looks like my final two answers here are +5/3 and -5/3. Letter D looks a lot to me like letter B. I don't have a GCF. I do have three terms. So again, I'm thinking somebody's FOIL problem. The only way I can make 3x squared is a 3x and an x. Now the 20 at the back is a little more complicated. There's lots of ways to multiply to get 20. I'm keeping my eye on that middle term, the -7. So, if I were to try like a 1 and a 20, there's just no way I'm going to make a 7 out of that, even if I switch places with the 1 and the 20. It seems like those two numbers are too far apart. Let's go the other direction. What if I did like a 4 and a 5? So if I put, say, a 4 here and a 5 here, let's see, that would give me a 15 for the outer and a 4 for the inner. I can't make a 7 out of a 4 and a 15, but I'm getting closer, and so that makes me think, well, what if I switch places with those two numbers? What if I put the 4 here and the 5 here? See, and I think that'll do it, because now I have a 12x for the outer and a 5x for the inner, I can make a 7 out of that. Now technically I want to make a negative 7, so I can do that with a negative here to make negative 12x and a positive here to make plus 5x. There's my negative 7x, and positive 5 times negative 4 is negative 20. So we factored. Now we set each factor equal to 0 and do our solving. And let's see here, subtract 5, add 4. The second one is finished. Divide this one by 3. And once again, we are done, and we have two answers. The final answers here, negative 5/3 and positive 4. Problem number 2. I've got this equation, cosine x equals a. A is just some number. We're being asked to find three different numbers, three different values that we could have there for a that would cause the equation to have no solution. All you have to do is think about the meaning of the x and the a. This is a trig equation. When I see cosine, what goes into it? Angles. So x is an angle. What comes out? Ratios. So a is a ratio. Well, if I want this equation to have no solution, I just need to put a ratio there that's impossible to obtain for cosine, like 2, for example, because the biggest cosine ratio there is 1. Any number for a bigger than 1 would lead to an impossible equation. Or I could use a number smaller than negative 1. Right? Negative 1 is the smallest cosine ratio, so negative 2, for example, would be impossible. There's tons and tons of numbers we could choose there. Anything outside of negative 1 to positive 1. Problem number 3, we want to rewrite each of these expressions so only sine is used of our 6 trig functions. We will simplify as long as we keep everything only with sine. So when I look at this first one in part A, I see a cosine squared x, and I'm immediately drawn to the Pythagorean identity. Sine squared plus cosine squared equals 1. Of course, I just have cosine squared x. Well, I can rewrite this so the cosine squared is by itself by simply moving that sine term to the other side. It's going to say cosine squared x equals 1 minus sine squared x. Well, now in my expression in part A, I have a way to replace the cosine squared x using only the sine function. Cosine squared x is equal to 1 minus sine squared x. Well, great. All I have to do is multiply this out, and I'm finished. I get 4 minus 4 sine squared x. Now, we're not saying that this is simpler than the original. I mean, the original looks a lot simpler than this, but that was not the directions. The directions change over to sine, and with sine, make it as simple as I can. And this is as simple as I can make it with the sine function. Letter B is a very quick one, because when I see cosecant, I know that I can simply reciprocate it to the bottom. As long as I don't have anything being added or subtracted, I can reciprocate it to the bottom, and it turns into the sine function. Of course, I've got a couple of them, so it'll be sine squared x. I don't have any way to simplify that, and so I'm finished. And then part C, let's see, when I see cotangent, of course, I'm thinking about the quotient identity. I could change this to be cosine squared x over sine squared x. So I'm on my way. I've got the sine function in there, but then I need some way to get rid of the cosine squared x. Well, I'll just do the same thing we did back in part A. I have a replacement for cosine squared x. It's that 1 minus sine squared x. And as soon as I fill that in, I'm done. I've rewritten the original expression so that only sine is used. Now, I suppose on this part C, you could go one step further and distribute that sine squared x into both pieces, which would result in 1 over sine squared x, and then minus 1 out here, because sine squared over sine squared would be 1. And I think that would be a fine answer as well. In fact, that makes me think of another way I could have done this. I could have used one of the Pythagorean identities. One of the Pythagorean identities says that cotangent squared is equal to cosecant squared x minus 1. If I had made that replacement first, I could have then changed cosecant squared to 1 over sine squared and obtained this answer here. So either of these two answers I think is fine. Problem number 4, back to algebra. We want to solve each of these radical equations. The way to solve an equation with a square root is to isolate the square root. That's already been done here. And then square both sides. Squaring is the opposite of square rooting. So when I square a square root, all I'm left with is what was inside there. The other side, of course, would be 25. And when I subtract 3 from both sides, I'm going to get a final answer here of 22. Now, square root equations, though, are notorious for what we call extraneous solutions, meaning you do all your algebra right, but the answer still doesn't work. So you have to, at the end, plug the number back into the equation and do a little check and make sure it actually comes out to be true. Let's see, if I put 22 in here, am I actually going to get 5 on the other side? I think I will. This will be square root of 25, and the square root of 25 is 5, so this is the solution. Watch what happens, though, on letter B. It looks very similar. I'll square both sides, and that'll give me x minus 3 here. Negative 4 times negative 4 is 16. I'll add 3 to both sides this time, and I get a final answer of 19. Except hold on, remember you got to check for those extraneous solutions, and see this time when you run the little check, if you plug 19 in for x, this side comes out to be square root of 16, which is positive 4, not negative 4, so it doesn't check. 19 is not the solution to this equation. In fact, then there is no solution to this equation. Why did that happen? Well, it's because the technique of squaring both sides loses information about negatives. When you square things, negatives tend to disappear. And so, sure, 19 is the solution to this little equation, but it is not the solution of the original. So don't forget to check those answers.